Welcome to Senior High School Math Series. Let us have representations of rational functions under General Mathematics Quarter 1 Week 2 based on Curriculum Implementation and Learning Management Matrix for K-12's most essential learning competencies. Here are our learning competencies. Represents rational function through its table of values, graphs, and equation. Finds the domain and range of rational function. Before we continue, let us ponder on this. The fear of the Lord is the beginning of wisdom, and the knowledge of the holy is understanding. This is from Proverbs chapter 9 verse 10 of the King James Bible. Let us have the definition of a rational function. A function of the form f of x is equal to p of x over q of x, where p of x and q of x are polynomial functions, and q of x is not equal to 0. Hence, let us recall the definition of polynomial functions. A polynomial function of degree n in the variable x is a function defined by p of x is equal to a sub n x raised to n plus a sub n minus 1 x raised to n minus 1 plus, in decreasing degree of x, a sub 1 x raised to 1 plus a sub 0, where a sub 0, a sub 1 until a sub n are elements of the real numbers, and a sub n is not equal to 0. Also, n is a whole number. In here, a sub n is the leading coefficient, a sub n x raised to n is the leading term, and a sub 0 is the constant term. For example, in the polynomial function p of x is equal to 6x cubed minus 3x squared plus 4x minus 5, 6 is the leading coefficient, 6x cubed is the leading term, and negative 5 is the constant term. In this polynomial function, we have 4 terms. Rational functions can be useful tools for representing real-life situations and for finding answers to real-world problems. Rational formulas that can model many real-life situations with one variable held constant can be used as rational functions. Example, the formula for the scalar quantity speed, that is s equals d over t, where s is the speed of a moving object, d is the distance covered, and t is time. With the distance held constant, s can be written as a function of t. Also, the formula for density of an object, d is equal to m over v, where d is the density of an object, m its mass, and v its volume. With the mass held constant, d can be written as a function of volume. The formula for rate, r is equal to w over t, where r is the rate, w is the amount of work done, and t is time. With the amount of work done held constant, r can be written as a function of t. And this is also true for some other rational formulas. Let us have example number 1. One of the most prestigious events in any athletic meet is the 100-meter dash. It has been contested at the Summer Olympics since 1896 for men and since 1928 for women. Represent the speed of a runner as a function of time it takes to run 100 meters in the track. For our solution, we're going to use the formula for speed, that is s is equal to d over t. In our problem, d is held constant, it says d is equal to 100 meters. Hence, we can write the speed as a function of time. S of t is equal to 100 over t. Let us have example number 2. Construct a table of values for the function in example number 1. Plot the points on a Cartesian plane and determine if the points follow a smooth curve or a straight line. From the function in example number 1, we have S of t is equal to 100 over t. Let t be the time in seconds, so that we will have the speed as meters per second. In physics, we learned that speed is a scalar quantity. It tells how fast an object is moving without saying anything about its direction. Hence, speed is always positive, so we'll take positive values for t so that the values for speed or S of t will be positive. We also know that from the rational expression 100 over t, t cannot be 0, else the function will be undefined. So let us have the values for t as equal to 0.5 second, 1 second, 2 seconds, 4 seconds, 8 seconds, 10, and 15 seconds. From our lesson in evaluation of function, to get the value of S of t, if t is equal to 0.5, so we have S of 0.5, that will be 100 over 0.5, and this is equal to 100 times the reciprocal of 0.5, or 1/2, that is 2 over 1. Hence, S of 0.5 is equal to 200. We do the same with the other values of t. If t is equal to 1, so we'll have 100 over 1, that is 100. If t is equal to 2, we have 100 over 2, that is 50. If t is equal to 4, 100 divided by 4 is 25, so S of t is 25. If t is equal to 8, then S of t is 100 over 8, that is 12.5. If t is equal to 10, then we have 100 divided by 10, that is 10. Also, when t is 15, we have 100 divided by 15 for S of t, that will be 6 2/3, or 6.67. Since we have values for t and S of t as positive, then we'll take the first quadrant of the Cartesian plane. Let us plot the points. When t is 0.5, S of t is 200. Our Cartesian plane do not have 200 on the y-axis or S of t. So we'll start with t is equal to 1 and S of t equals 100. That will be at coordinates 1, 100. T is equal to 2 and S of t is equal to 50. So we have 2, 50. Next, the coordinates 4, 25. Next is 8, 12.5. Then we have 10, 10. Then we have 15, 6.67. As we can see, as the value of t increases, the value of S of t decreases, and it appears that as t increases to infinity, S of t approaches 0. So from the points plotted on the Cartesian plane, we see that the graph follow a smooth curve and not a straight line. Let us have example number 3. Represent the rational function f of x is equal to x plus 1 over x minus 1 using a table of values, and plot a graph of the function by connecting points. Notice in the function that substituting x equals 1 will make the denominator 0. Hence, x cannot be equal to 1 as it makes the function undefined. So for the values of x, we will choose some values to the left of 1. We'll have negative 10, negative 5, negative 1, 0, and 0.5. So from negative 10, we choose values approaching 1 from the left. And to the right of 1, we will choose 1.5, 3, 8, and 15. Then we will get the values of f of x by substituting the values of x to the function. We start with x is equal to 10, so we'll have f of negative 10, that will be negative 10 plus 1 over negative 10 minus 1. And this is equal to negative 9 over negative 11, so that will be 9 over 11. If x is equal to negative 5, so we'll have f of negative 5. This will be equal to negative 5 plus 1 over negative 5 minus 1. And this will be negative 4 over negative 6. We can simplify that as 2/3. If x is equal to negative 1, we will have f of negative 1, negative 1 plus 1, and in the denominator, negative 1 minus 1. So this is equal to 0 over negative 2. Hence, if x is equal to negative 1, f of x is 0. And for x is equal to 0, we'll have f of 0. That will be 0 plus 1 over 0 minus 1. And we have 1 over negative 1, that will be negative 1. Now, if x is equal to 0.5, f of x, or f of 0.5, will have 0.5 plus 1 over 0.5 minus 1. This is 1.5 over negative 0.5. 1.5 over negative 0.5. And that is equal to negative 3. Next, if x is equal to 1.5, we'll have f of 1.5. That will be 1.5 plus 1 over 1.5 minus 1. This is equal to 2.5 over 0.5, and that is equal to 5. Next, x is equal to 3, so we have f of 3, 3 plus 1 over 3 minus 1, that is 4 over 2. Then f of x is equal to 2. If x is equal to 8, we'll have f of 8 is equal to 8 plus 1 over 8 minus 1, that is 9 over 7. And if x is equal to 15, we'll have f of 15, so we'll have 15 plus 1 over 15 minus 1, and this is 16 over 14. Then this can be simplified as 8 over 7. Let us proceed to plotting the points obtained for the function f of x is equal to x plus 1 over x minus 1. Let us start with the coordinates negative 10, 9 over 11. So that will be negative 10, 9 over 11. Next is negative 5 2/3. And then we have negative 1 0. Next is 0 negative 1. And then we have 0.5 negative 3. Notice that as the value of x increases, the value of y decreases. And also, as x approaches 1 from the left, the value of y decreases. We did not choose x is equal to 1 because from the function, we saw that x is equal to 1 will make the function undefined. So, the graph of the function does not cross or does not intersect the vertical line x is equal to 1. For the next value of x, we chose 1.5 and f of x is equal to 5. So we have 1.5, 5. The next coordinates, we have 3, 2. Then we have 8, 9 sevenths. And then also the last coordinates is 15, 8 over 7. Notice that to the right of 1, as the value of x increases, the value of y decreases. Another notable situation in the points plotted is that the value of f of x seems to approach the line y is equal to 1. So we have the smooth curve showing the graph of the function f of x is equal to x plus 1 over x minus 1. Notice also that as the value of x approaches 1 from the right, the value of the function reaches a very high value, or f of x reaches a very high value. And also as the value of x approaches x equals 1 from the left, the value of f of x or the function reaches a very low value. This time, let us have the domain of a rational function. We know that the domain of a function is the set of all values that the variable x can take. Hence, the domain of a rational function consists of all the real number x except for those for which the denominator is 0. Let us have an example. Identify the domain of the function f of x is equal to 1 over x minus 4 plus 3. Now we know that the domain of a rational function is the set of all values that the variable x can take, and that will make f of x a real number. Hence, to get the domain of f of x, we find all those values that will make the denominator 0, and these values are not included in the domain of the function. So we have the denominator x minus 4 should not be 0. Adding 4 to both sides, x is not equal to 4. Hence, the domain of the function f are all real number x such that x is not equal to 4. The range of a rational function consists of all real numbers that f of x will take. One way to find the range of a rational function is to find the domain of its inverse function. Let us have an example. Find the range of the function f of x is equal to x plus 1 over x minus 4. So to find the range of the function f of x, we need to find the domain of its inverse function. And to do that, we'll get the inverse of this rational function. Let us recall the methods of finding the inverse function. So to do that, we write f of x as equal to y Then we have x plus 1 over x minus 4. The next is to interchange the variables x and y. Hence, we will have x is equal to y plus 1 over y minus 4. The next procedure is to solve for y in terms of x in the resulting equation. Multiplying both sides by y minus 4, we'll have xy minus 4x is equal to y plus 1. Writing the equation in such a way that all terms with y variable be on the left side and those without the y variable be on the right side. So we subtract y from both sides of the equation. We will have xy minus y. Also, we add 4x to both sides of the equation. We'll have 4x plus 1. On the left-hand side of the equation, y is a common monomial factor. So we have y times the quantity x minus 1 is equal to 4x plus 1. Now we can divide both sides by x minus 1 such that we will have the equation for y in terms of x. Then we have y is equal to 4x plus 1 over x minus 1. In the previous slide, it says that the range of the given rational function is the domain of its inverse function. Hence, the domain of its inverse function are all values of x such that x is not equal to 1, or x minus 1 should not be equal to 0. Therefore, the domain of this inverse function are all values of x, or all real values of x, such that x is not equal to 1. Therefore, the range of the given function are all real numbers y, such that y is not equal to 1. Let us have another example. Find the domain and range of the function f of x is equal to x minus 2 over x plus 3. For our solution, let us start with finding the domain of the function. So for the domain, we'll have all real values of x such that x plus 3 is not equal to 0. Subtracting 3 from both sides of this, we'll have x is not equal to negative 3. Hence, the domain of the function f are all real values of x such that x is not equal to negative 3. For the range of this function, we're going to find the domain of the inverse function. So we'll have y is equal to x minus 2 over x plus 3. We interchange the variables x and y, so we'll have x is equal to y minus 2 over y plus 3. Multiplying both sides by y plus 3, we'll have xy plus 3x is equal to y minus 2. Collecting all terms with the y variable on the left hand side, we'll have to subtract y from both sides, so xy minus y. Also subtract 3x from both sides, we'll have negative 3x minus 2. On the left hand side, we'll have y times the quantity x minus 1 is equal to negative 3x minus 2. Writing the equation for y in terms of the variable x, we'll have y is equal to negative 3x minus 2 over x minus 1. Again, the domain of this inverse function is that x minus 1 is not equal to 0, hence x is not equal to 1. Therefore, the range of the function f, or the original rational function f, are all real values of y, such that y is not equal to 1. Another way to find the range of a rational function is to plot the graph of the rational function, and from the graph we'll be able to determine the range of the rational function. That will be all. Exercises on this topic may be downloaded from the link given on the description of this video. Thank you for watching. Please subscribe for more math lessons.